Quantum computing is a completely new paradigm for doing computation that hopefully will allow us to solve problems that are completely intractable with the conventional computers we have to date. My name is Alejandro Perdomo. I'm a research scientist in the Quantum Artificial Intelligence Laboratory here at NASA Ames Research Center. NASA's Quantum Artificial Intelligence Laboratory is interested in two main tracks of research. One of them deals with the practical aspect of taking NASA applications to the quantum device and solving it with the quantum device. The second track is more like physics-based and really like basic science type of questions where we try to identify how is quantum mechanics doing its magic to solve these problems faster than otherwise with a standard conventional computer. During the first period as a research scientist at NASA, I was more interested in understanding the physics of the device, in the sense that we wanted to really identify where quantum tunneling, for instance, is extremely important for solving problems. So the question is, how does it work, and how can we see it more often? In which problem instance will take advantage of quantum tunneling? So that's the first area of research that I did. Nowadays, I'm more focused on the application side. Applications encompassing a very broad concept, like all the way from taking several computational problems, hard NASA computational problems, into the quantum device, and then this process of mapping a computational problem into the device is a very hard task in itself. So it's an art, actually, how you take a problem that is, it could be mathematically kind of like loosely defined or even just in words, and then take this problem to the machine language that the quantum device that we have here actually understand. Is not a straightforward task. And even when you are programming the quantum device itself, there are a lot of degrees of freedom that actually you can play with. And which ones are the optimal parameters for this? We just don't know. So the question is, how can you recognize the best settings for the quantum computer to operate on a certain application? That's another research direction that I've been pushing to. In the case of the quantum computer we have here housed at NASA Ames, the quantum computer is made of superconducting qubits. These basically are just metal wires of niobium that when they are chilled to very, very cold temperatures, almost absolutely 0 Kelvin, you see that actually these little wires of metal behave in this awkward manner, where you can have quantum superpositions, where you can have that the current in these wires are going counterclockwise and clockwise at the same time. You can have quantum tunneling. Maybe you have the wire going in one direction and out of the sudden the wire is going in the other direction, just with not having even sufficient energy for this transition to happen. So all these kind of properties happen at this very microscopic scale. From the implementation that we work here at NASA, the type of algorithm is aimed only to solve optimization type of problems. Any problem that you can phrase as reducing the cost or reducing the energy of a certain function. If you want to design the best air traffic that is coming into an airport, and then all the time schedules, all the time constraints, so optimizing in such a way that you get the best out of the scheduling, that's one of the applications that you can do with a quantum computer. Another application would be in the fields of astrobiology. Modern biology nowadays uses a lot of techniques from synthetic biology and from the genomic era. Genome sequencing is a hard computational task. When you sequence the genome of a certain microorganism, for instance, you're getting a lot of data. And breaking that data and putting together this puzzle into the final genome for that microorganism. This is the type of task, for instance, that you could do with a quantum computer. You could do genome sequencing. So another application is in the field of fault management. So imagine that you have a complex engineering network. There are a lot of different little components in this complex system that if any one of these fail, then in principle you could have a catastrophic effect. So detecting faults as they happen and detecting faults in this large system is another intractable problem. because there are so many combinations that you can try that could possibly explain the outcome that you are seeing, that actually going over all these possible combinations is an intractable problem. We believe that in the next 5 years to 10 years, we can actually, I think it's a feasible roadmap to having some problems, at least some certain specific problems that are very hard to solve with conventional computers or even with supercomputing centers, that actually you might have an advantage by using a quantum device.